Welcome back to I'm finally reading my brother's book. I'm Clay Bascom, here with my brother Gavin Bascom, theoretical chemist and author of On the Inside of a Marble. In today's episode, we're diving into the two most mysterious players in the cosmos, dark matter and dark energy. Why do we call them dark? How much of the universe do they actually make up? And what do they reveal about the story we tell ourselves about the universe's history and the limits of that story? Along the way, we'll tackle quantum inflation and why both Gavin and I feel such a deep need to understand the universe, even if it means staring into the dark. Let's get into it. We're back.
What up?
We're going to talk about some dark stuff. We're talking about some stuff that doesn't reflect light.
Right, that kind of dark, not like Fargo dark.
True.
Yeah.
So, yeah, this is really interesting. I knew about dark energy and dark matter, and I don't think I understood it. And one thing that I did Google pretty quickly was I was like, why doesn't light interact with dark matter or dark energy? Like, why not? Why doesn't it hit it?
It's a little bit of a tautology, right? Because that's the definition of it. So
Well, the internet told me that it was because dark matter and dark energy don't have a charge. I didn't actually know that apparently photons can only interact with things that have some kind of charge.
well, dark energy definitely doesn't have a charge because we don't know what it is. And it doesn't
Right.
seem to have
Well,
anything.
Yeah. Dark energy seems to be more of a math placeholder
Yes.
if I had to
Yeah.
bet on it.
Yeah. We'll talk
Whereas,
about it.
yeah, whereas dark matter seems like we can actually see it. Well, we can't see it, but we can see it curve light. So it's like it's there.
Yeah, it's definitely there. It just seems to be like some sort of coal
Yeah.
dark mesh.
So let's
that
take a
sucks
step
stuff
back
out.
now and say, what you explain? You're the scientist. You went to school.
Why don't we
What is
actually?
dark matter? And why does it
We
matter?
just went straight in. So we're in chapter 5. Chapter 5 is called "The Universe Far from Equilibrium."
Nope, we're not. We're
Sorry,
chapter
nope.
6, bro.
Sorry, we're chapter 6. Sorry.
Cut that.
I just had my book open to the wrong page. Okay, we're in chapter 6. It's called "The Statistical Mechanical."
So much planning goes into these podcast episodes, guys. You're getting a little behind the scenes. Our notes. We don't have notes.
Yeah, right. Well, the notes are the book. That's kind of the whole point. Anyway, so the topics we're going to cover are dark matter, dark energy. Then we're going to do a little tiny history of the universe as we know it, which upon rereading this, I'm like, this could have been chapter 1, probably.
Yeah, actually, this was very readable. I was like geared up for like another like, I'm gonna read this 10 times and it'd be so confusing. I was like, this was easy. I get this. This is pretty good. Although you did lose me a few times and I was so nice, but I wrote down next to those what so that you can explain to me what was happening. But yeah, I mean, I didn't jump off too into the deep end. It says dark energy and dark matter on the first page of the chapter.
Yeah. Right. And then I just like to give a little review, but then we're going to go through what actually was probably the most rewarding section of the book to write, which is like my theory / understanding of what particles actually are and like what forces actually are.
Definitely where you lost me. So it'll be fun
We
to get into.
finally got there.
Woo.
Okay, cool. Yeah, no, actually, let's do it the other way. So we talked about dark matter, which dark matter is just the example I give is that when you look at how fast galaxies are rotating, we can measure how fast they're rotating, and then we can count up all the stuff we can see. And it's not exact, but you can see enough stuff that you can basically get an estimate of the density of the galaxies, and then you can calculate how fast they should, like what's their max speed of rotation, because if they spin too fast and they have too little mass in there, then everything will fly out, right? There's like centripetal force.
Correct.
So you can measure, and then when we do this calculation, you do it for one galaxy and it's like, well, where's all the mass? Like it's going way too fast.
Yeah, so it's like basically you could also talk about it like if you're spinning a tennis ball attached to a string, what would be the speed that you have to swing the tennis ball where the string would break? And all of the galaxies that we've measured are spinning fast enough that the string should break. Like the galaxy should rip apart.
Yeah.
It should, like the gravity shouldn't be strong enough to keep all of the stars and all of the stuff together. It should be, rapidly expanding away from each other. It's not. So then you kind of, I'm assuming some very smart mathematicians back in the day reverse engineered it and said, oh yeah, this is how much mass is missing.
Yeah. You have to go backwards and say, okay, well, there's more mass in there. That's the answer.
Yeah. For it to be spinning that quick, it has to be this much dark matter in that galaxy to keep it from ripping apart. And that means that there's some kind of matter out there that light doesn't interact with, meaning we can't shine a flashlight on it and nothing happens. No.
Yeah, it doesn't have the electromagnetic properties that the rest of the things do.
I knew about dark matter, but I thought dark matter was the same as dark energy, and we'll talk about dark energy in a minute, was that it was a placeholder, that I didn't think it was an actual thing. And it was interesting in your book, you talked about how we've actually measured light being bent around dark matter. So dark matter
Yes.
has gravity. That's been proven. I didn't realize that. I always thought it was one of those things where it was like, we haven't figured out why this trick of the universe is happening. And I thought it would be one of those things. Oh, actually, turns out there's gravity in the cracks, or I don't know, something weird was happening. And there wasn't actually something like dark matter out there.
Dark energy is like that. It's like some sort of placeholder gravity in the cracks type thing. But the dark matter is not. It's very much a real thing that we can measure. Like you say, it was originally inferred because of the rotation of galaxies, but then we can also use this thing called gravitational lensing, which is if there's matter out there, it should have gravity. And then the gravity, when light goes through gravity, it bends a little bit. So because of warp space time, and that was relativity, it was Einstein's original thing. But so there's these really cool pictures you can look up online of galaxies that are like split up. There's like, it looks like four different pieces of galaxies, but it's actually just one because there's a black hole or there's some like big piece of mass that has bent the light around it. So it almost looks like you're looking through like a looking glass, like a convex glass. And then it turns out if we like point our telescopes and look for gravitational lensing, it's like everywhere. And there's dark matter like everywhere. And you get this wild picture that emerges of this sort of fibrous background to the cosmos of
That's
these,
crazy.
and you can look up these images online. They're wildly cool. It's almost like, when you go, or you and I took a trip, we took a family trip to the Canadian Rockies, and when I was there last summer, this summer actually, and and we were there, I was just like struck. Like, it's beautiful, and it's going to be beautiful. But what really moved me was the way that you can see the history of the mountain range. It's all just like there, right? These mountains are old. They're
Yeah,
so old.
specifically went to Banff National Park,
Yeah.
and you can like see the layers of rocks. I remember pointing it to one of my nieces and being like, "Look, you can literally see like it took millions of years for this mountain to get pushed up, and you can
Hmm.
see all the different layers. And like that layer right there, that was marine life. That was under the ocean millions of years ago." And she looked at me like, "I don't care. I want to get to the coffee shop." I'm like, "Okay, that's okay. We're
Yeah, we
teenagers."
all wanna get to the coffee shop, but it's just so breathtaking to see the history and such an old, deep history, like, splayed out for you, and that's the vibe that I get when I look. I mean, they're rendered images, like, they're simulations, but it's still, like, it's the best we can do at sort of understanding what the.
She's slinging AI on here.
No, not AI. They're engineered images, like the same way that we talked about in the book, that use you can take a bunch of different measurements and then you can like put it all back together into a 3D image.
So I had a thought, and you can probably just be like, "No, Clay, you're not a scientist. You are wrong." But I had a thought. It was interesting, and I was like, "Okay, so we have all this matter is out there." And this is before I looked up and was like, "How come there's energy that could possibly not interact with light?" The only thing I can think of that's like that are black holes. And then I thought, well, something I've learned about black holes. It's interesting to talk about in the podcast is that we first theorized that black holes existed because we thought of a supernova, and we knew that like some supernovas would be so big that it would turn in on itself and that to go to a singularity. Some scientists at the time said, no, there's not possible. There's got to be some reason why that doesn't actually happen. Black holes don't
Mhm.
make sense mathematically. Turns out those guys are wrong. Black holes do exist. But then we were like, hey, wait a second. There might be black holes at the center of galaxies that are massive, massive, massive. They're a lot bigger than the mass hole that would be produced with a supernova, right? Or a star collapsing in on itself. So then you have to wonder, well, where did those supermassive black holes come from? Well, then we think, oh, they must be other black holes like combining. That's the only way we could think of it. But then you say, okay, well, then there's like a certain size a black hole has to be, but we've actually seen black holes that are smaller than the size of the star
Mm.
collapsing in on itself. So then it's like, well, really, where those black holes come from? And, like that's kind of crazy. So then I had a thought like, well, what if there's just things happening in the universe that we've never witnessed for whatever reason that are producing lots of little black holes, just like little guys? Because the theoretical, like smallest a black hole can be is actually quite small. I knew that from science fiction. A lot of people talk about, oh, you could technically make a very small black hole. That wouldn't necessarily interact with the environment too much around it until you got too close or whatever. But so I know theoretically speaking, black holes can be small. I don't know, like teeny tiny, but
I
it
don't
can
know
be much
how
smaller.
small. This is something we should look
I
up, but
I did look this up once, and it was like, you know, it was one of those things where the actual mass was still a lot. It was like you had to be like a moon-sized amount of mass, but it would take up like, the teeny tiny prick of actual thing, and so his actual event horizon would be absolutely tiny. But like that's theoretically that's all the mass you would need. We need because it's the mass you actually have the pressure to push the mass into the small enough
right,
point, right? And so
right.
then it collapses in on itself. So it take a massive amount of energy to be able to create that kind of pressure. But what if that's happening somewhere in the universe under different weird circumstances that we've never seen? And so actually dark matter was just a bunch of little black holes.
Bunch of little black holes. I think it's a cool theory. I think if my memory serves me correctly, we initially underestimated the size of. I think you said this even. We underestimated the size of the black holes in the center of
Hmm.
galaxies.
Yeah.
And as we sort of got better measurements, we understood there was a lot more, and that did account for some of the dark matter. Right. So,
Mm,
so some of the dark matter is just more black holes and bigger black holes than we thought. But I
yeah.
think it's important to underscore like the black holes can get gigantic. They
Yeah.
can get so big, bigger than billions
Well,
of suns or
as
whatever.
big as our entire universe, because that's our universe is inside of a
Go
black
way
hole.
all the way back to the yeah. Very nice callback.
See what I did there.
Yeah, no, I think that's an interesting I think that even if something was small, like as small as a penny or whatever it'd have to be, I think it would still have a pretty big signature, although
Right.
maybe not. I don't
I
know.
don't know. Well, once I realized that light will not interact with something that doesn't have a charge, then it's like, oh, okay, that
Mhm.
that makes sense. Then like
Yep.
there can
Just
definitely
something
be
without charge.
matter out there that doesn't have a charge. Well, just to jump forward a little bit, but do we understand how much of what this matter we're talking about is that dark matter probably makes up about 27% or so of or 26.8% to get more precise, of the energy or the matter in the universe. And then normal matter only takes up
Go ahead.
5%
Yeah,
or 4.9%, which is absolutely bonkers that we can
think
only
about that.
look at 4.9%. And the rest is CDM, AKA dark energy,
We
which
have
is
no idea.
absolutely wild. So, like 68.3% of our universe is a placeholder. What?
Don't no clue. We have no clue what it is. There's a very fun science story involving Einstein, so like I go into a little bit more detail in the book. Initially when they were working on he was working with a lot of people on this to extend special relativity to general relativity. And he had to put in a placeholder because he was trying to do the math right. And he thought, okay, we have a stationary universe that's obviously not moving or expanding or anything like that, which was actually a bad assumption to make, but that's just the one that he made. And so he put in a thing called the cosmological constant into the equation, the universe equation. And later he called it his greatest blunder because he just made a bad assumption. And it wasn't that long. It was during his life. It wasn't that long later that Edwin Hubble figured out that no, actually the universe is expanding, space is expanding, because that's what it did. It held the universe sort of constant in like a flat, nice, tidy universe.
Well, he had it on the wrong side of the equation,
Well,
right?
that's the cool part of the story is that we assumed because of Hubble's constant that it was that the universe is speeding up, that the expansion is a sort of constant expansion, which would require there to be the constant, I think, on the same side of the equation that he had it at. But then later, much more recent, actually more like in our lifetime, I saw Perlmutter and these other guys got the Nobel Prize for using advanced computation plus really powerful telescopes to measure a lot further back into the early universe and just do the same calculation that Hubble did. So measure the expansion of the universe, but further back. And what you assume is that there's going to be this sort of like constant rate of expansion all the way back. And it turns out that's not how it works at all. There was a speed up and a slow down and then a speed up again. And it's like so mind boggling.
Yeah.
And this is what I talk about when I'm talking about like the history of the universe is so like it's just laid out and you can see it, but it's such vast cosmic scales that we're talking about. But anyway, the thing with Einstein that goes back to say, yes, it was right to have the constant, but like you said, it's on the wrong side of the equation or the sign was flipped. And that leads to this sort of crazy stuff. There's also a fun documentary about that part when I think it's really silly, but it's like there's a thing in physics called a jerk, which is when you change acceleration, like when you change the direction. So when you're going from you're going one direction to the other in terms of the speed, that's called a jerk. And
Freaking jerks.
so there was a headline cosmic jerk announced or cosmic jerk discovered. And it was like a direct reference to the
Eh,
guy that was working on it.
it's pretty good.
Anyway, yeah.
Well, yeah, no, that's pretty interesting. And we'll get back to the history of the universe and the whole
Yeah.
it was a single point and then
Right.
plasma and then speed up real good and go
But
back down.
yeah, but to get to the point, that's what dark energy is. That's the definition of it. Is it's like something that is making the universe rate of expansion speed up.
Yeah. So, like, in other words, we know through observation by looking out at everything. I enjoy this thing. It's like if you were a raisin inside of a loaf of bread, and
Mhm.
if somebody puts you in the oven, and the bread starts to expand. If you were to, if the raisin was able to look out and be like, oh, I'm going to measure how far away from I are from the other raisins, there would be this inflation of like it's getting farther and farther away, faster and faster. That's happening to us when we look out at the other galaxies. They are expanding away from us faster and faster, which is another way of
It's
saying
that they are receding away from us,
yes.
yeah.
Yeah, at an
And
accelerated rate, right?
they're accelerating, which is weird.
Yeah, which is strange.
But the thing that, the other part of that I talk about in the book is like it'd be like throwing a baseball and it like slows down and then breaks gravitational and then starts speeding up again once it gets into outer space.
Right,
That's what it seems like the universe did. Is it like the inflation refers to the very, very early universe when space expanded so fast that it was like a bomb going off. But
right.
it was like a space bomb, which is I don't know, maybe that should be like a cool band name or
Well,
something.
though, that makes you think of just bombs going off in space. This is like, no, space was the bomb.
Yeah, like space is the bomb. Um going off and then it slowed down and then it sped up again.
Yeah,
Who
and
knows? Who
and
knows why?
when you break the math down to be like, all right, how much energy out there would it take to make the universe expand like that? It's 68% of all of
Of
it.
all the known mass in the universe because you can measure the mass of the universe, roughly, you can estimate it.
Yeah. So it's like if you wanted to know how much, or just like a good example that you can point to this when you really want to say to someone, look how much we don't know.
Yeah.
68% of the universe
Yeah.
energy is just should be there. We can't see it. Don't know. It's dark energy.
Yeah. We're just
Yeah.
we're inferring its existence, yeah.
Yeah. So that's the one where I'm like, I think, yeah, there may come a time when someone really smart or maybe an AGI or something will be like, oh, you're looking at it backwards. It's actually this. It's this thing that you've known about this whole time, but you're looking at it weird, and so you don't think it's doing the thing it's doing. It's like, oh,
Yeah.
gravity actually has two sides. One side pulls.
Well, yeah, there are people it doesn't take artificial intelligence to get there. There are really smart people that have theories about this that have been working on them. They're just fiendishly hard to test and
Yeah,
prove,
yeah. So
but they're out there.
let's go to the narrative history of the universe. We talk a lot about how you can only engineer a version of the universe, and how really our understanding of the Big Bang is more like reading a recipe than it is like a narrative deterministic view. But being able to use the engineering view gives us the ability to sort of put together a fun little narrative, and that's what Gavin has done in this chapter. Is he puts together the history of the Big Bang. So let's hear it from the author's lips.
It's a good read. It
Yeah.
was nice to read it, but yeah, I instead of saying it's more like a recipe, I think a more precise way to put it would be that it's we like people took videos of it, but they're all out of order and they're not labeled. So you have like tons and tons of little tiny clips of things, and now your job is to engineer or recipe it all into one story.
Right.
And we spent a lot of time explaining in the first couple of chapters like why that order will never ever be absolute. Like you'll never ever be able to say this led to that, to that led to that in any sort of deterministic way. But what you can do is just sort of guess based on the probabilities frameworks. Okay, well, this particular event only happens in these conditions. So, it's unlikely that there's plasma out in empty space unless there's like really, really high gravity and then you can have enough energy to strip the electrons off or whatever. So we can engineer a narrative view, and the one that has evolved is really fun and interesting.
Give it to me.
Yeah, it's basically that this space bomb went up, like everything was super dense and hot, and we have no idea what was going on because we can't see back that far, but we can infer that it was all super dense and hot. And there were some quantum indeterminacies that you still have to account for because they're always everywhere, no matter what. And then the space bomb went off, and space itself expanded so fast, and this is Alan Guss' inflationary theory, expanded so fast that it like spread out all of the plasma which cooled it off quite a bit. And that cooling down meant that the quantum indeterminacies could and also spread them out. So they're colder and more spread out, which meant that they could have more of an effect on everyday life. And those
Just
of
picturing atoms getting up to go to work. Yeah,
yeah.
oh no, the quantum entanglement are getting me today.
And like the light left over from that expansion is the CMB, the cosmic microwave background. Then there's a real long empty gap where we're like, okay, from there, that only produced, or we assume that there only existed because it's 99.99% of the material in the universe is all basically hydrogen or helium, which is just one proton or two protons sticking together with a couple electrons. And so the theory is that it was all plasmified, which means the electrons weren't even on their parent atoms at all. They're all just kind of moving around because it was so hot in the dense part. But then when it got spread out, then they could start to, because it was also uniform, and the CMB is so uniform when you measure it that it doesn't make any sense that there could be any sort of narrative history there. It was all just hot, dense, that's it. So then the theory is that space expanded so fast that regular rules of hot, dense things don't apply, and then quantum things start to apply in a way that's meaningful. And so you can have inhomogeneous densities, which we then do a whole lot of this. We hand wave that into, then you get galaxies, right? Because they must have sort of just coalesced into stars eventually, or nebulae, and then the stars start igniting, and then the stars go off, because we know stars are there because we see them. So we know at some point the stars have to show up, right? And we get stars, and then this was hand waving, by the way. This wasn't like washing a car.
No, I thought it was a magic trick.
Well, sure, best that would work too. And we know that the heavy elements are formed in the stars, which is also a really cool thing. That's true. So, all the stuff that we enjoy, all the metals and all the rock and dirt and the cells that you're made of, and all that's all made of heavier elements like carbon, and all those elements can only form under star-like conditions. And then when stars go supernova, they eject all that stuff, all this trace amounts of heavy metals that can form inside the stars. They eject them out into space, and then over eons and eons, those collect into planets, rocky planets, where you can have life.
So this is something the James Webb Telescope is doing a lot of, is trying to take a look at really early stuff in the universe, which is why I think the last couple of years you've seen quite a few headlines that, physics is being rewritten. It's like, well, not rewritten, but lots of that hand waving is now coming under scrutiny.
Yeah, right.
People are going, wait a minute.
Well, maybe there's
You said there weren't any black holes until at least this point, and now we're seeing them
Right.
already. Like, oh,
Right,
well,
right.
yeah, we didn't know. We didn't think they could have a black hole at that point. Turns out it can. If you get enough helium together, they have a big old party black hole.
Get enough of anything, squish it into small enough spaces, you can get black holes. First you get atom
Yeah.
bombs, but then eventually you get black
Boom.
holes. Yeah,
Well, no, an atom bomb is a fission reactor. You've got
sure.
don't get a lot of fission. You get a lot of fusion.
Sure, that's true. That's correct. Yeah, so that's more or less the history narrative as we know it. Then we get to a coherently concurrent universe. So what did you take away from this chapter, from this section?
From the narrative part.
Sure, we'll do
I
that, but I
was-
was asking about the next part, but yeah.
Oh, from the narrative part, I was familiar with that. I had heard about the inflation, but I don't think I had understood that it was so rapid and that it was like that. It's that we needed that. I thought it was more of like a uniform expansion. Like it started expanding, and we've been expanding ever since. I didn't realize there was this extremely quick, rapid expansion, and then it slowed down, and now we're speeding back up again. That was a surprise. I didn't know that. And it was interesting that we still haven't actually proved that. Like it makes a lot of sense mathematically. There are observations that we could do, and he talked about some of those experiments in the book. As of today, which I did Google because this book came out 10 years ago. I did Google it to be like, hey, maybe in the last 10 years we figured this out. Turns out, no, we're still looking. They have launched.
Just all these things move it pretty slow.
Yeah, I think by the time your book had come out, they were on iteration 2. Now they're on, I think they've had 2 or 3 more iterations since then of getting their, instruments more and more precise and trying to measure gravitational waves. And they have not yet been able to do so, but I do think eventually we probably will. This is one of those things where it's like, the math works out so well. You were really just waiting for it to be confirmed more than we're thinking. There's a lot less chance that it doesn't exist. But who knows? Maybe it's wrong, and we'll figure that out.
But I will say, I think this. I agree. I think this will be confirmed. But I I want to say this is not a unification theory. Like
No.
this doesn't give us, how does quantum lead to gravity? Like that doesn't give us that.
Oh, so the next part of the book is the part that I was not super clear on. This is the part where it's a couple pages in, I was like, I don't know what's going on. But before we jump into that, I did want to say, it's good to know that you are as dyslexic as I am
Ah,
because you do. Did you see the typo? There's a typo in here.
well, there's
With
plenty.
the first time you mentioned dark energy, you said it makes up 63.8% with 68.3. And then, like, on the page next to it, you say it's 68.3 correctly. But that did throw me for a loop because then I Googled it, I just in wanting to research more, and it said 68.3. And I was like, oh, wait, did they
Instead
up
of
it?
63.8.
Yeah, you just transposed the 3 and the
Funny.
8.
Okay.
But I'm dyslexic. My dad is dyslexic. So it
Gotta
runs in
go
the family.
call my editors. That's their job.
Yeah, I've caught a few things in here that I was like, "Ooh, an editor would have known to."
I know there was editing, but it wasn't quite as good as it could have been. Anyway,
Yeah.
yeah, like
So yeah, break that down. A coherently concurrent universe.
I really hope that this is becoming clear to somebody by now. Okay, we've done a lot of like going inside of things here. We go inside the marble, then we go inside the swimming pool, then we go inside the wave function, the wave equation, then we went inside like friction. We are trying to understand friction. All of it is me doggedly trying to get at what the act of measurement is across spatial scales and what the act of sort of understanding the negative space of measurements. Because you remember we talked about space and we're like, what is space? You're like, well, it's what's not there. And you're like, well, that's a weird way to define something
Yeah. Also, it has a
because
temperature.
it's just, we'll get into that in a second, right? So, but basically, when you go to make a measurement, we sort of always default to thinking like we're just measuring the thing that we're interested in, like the weight or the velocity or the whatever. But when you're making measurements this precise, you have to actually include all the things that it should have done, but then it didn't. Oftentimes, that's what the measurement is. It's like it had I'm looking for a change in velocity. So it was supposed to stay, at this one constant rate, and then it like suddenly didn't do that anymore. And that's what I'm looking for. It's that
Right. You
like
call
loss
those
of
skips in the
yeah,
book.
well, yeah. In this chapter, I call them skips, and I get we'll get into that analogy in a second. But that's what I want to like keep in mind here is that we learned to embrace two fundamental things throughout the book so far. One is that when the math breaks down, or let's put it this way, causality breaks down in a way that is not physically possible, in a way that we could understand in our universe and our any sort of measurement that we've ever seen before. That is oftentimes what we're looking for to measure. And there's two ways that that could happen. One is that like energy sort of spontaneously jumps from one place to the next, like a skip, like in the narrative, in the story. It just like pop, what? That wasn't supposed to happen. And we're so used to it that we just call it something else. We just give it a name and we move on because it's like actually very pervasive and it's happening all the time, no matter what. Then there's another one, which is like, I can only keep track of where atoms are if I know like there's like a weird symmetry to information gathering that sometimes it's like, okay, I took a marker at point A, and then when it went off, it didn't go to point B. So instead it went to point C. So then I know that there's something about point A that I can like deduce about it. And so that sort of across spatial measurement can also be across time. It's like, well, I was waiting for it to complete this measurement and it didn't complete that measurement. And sometimes it's those kinds of skips. It's like it was supposed to be moving at this rate, and then it by the time it got there, it now suddenly had like a backwards spin. Like, we don't,
Right.
which that could be a spatial thing, but that also just be the frame rate thing too. Like the frame rate of that particular atom was changing in that particular. And so all of these like weird skips and inconsistencies in what would otherwise be like a cohesive and easy to calculate framework using normal Newtonian physics. Those are the things we're keeping track of when we
Mhm.
do quantum field
Yeah.
theory.
And trying to figure out whether it's just the process of measuring that's causing these skips or if it's
Or
something
or
more
is the
fundamental.
I'd say the other way around. When you measure it, if it's a fundamental thing, meaning it's true for all kinds of particles and I can find it happening all the time, and I can actually write down laws about when it happens, when it doesn't happen, that's fundamental.
Mhm.
But when it happens and you're like, oh, that's weird. I was not expecting that. Then it's probably something wrong with your theory. Then you have to go back
Mm.
and like rewrite the theory, or like I was just doing the math wrong, or like so it's very frustrating, right? Too,
Right.
right?
Or you're
To
measuring wrong.
because you're inside the measurement. Everything is inside the measurement. You're inside, so the strange loop necessitates that everything has to be put in terms of other types of measurements. So everything has to be, so and then there's that like semiotic drift problem, and there's all these other things to worry about. So then the analogy will come up with the book, and this is I'm really, really proud of this one. And I'll save you all this stuff about silicone and glass and sand or whatever, and we'll just get to the meat of it.
I love silicone. We can do silicone.
If you want to read we can go back. If you want more, then go back to the book. But here's the analogy: you're sitting on the couch, and this has happened to me before. This is why this has came to mind. You're sitting on the couch, and you hear like the wall creaking. How do you know? So like basically, okay, so there's a pop. There's some sort of pop crack thing.
Old house.
Immediately, you know that something is moving that was not supposed to move, and you can look around, and there's no obvious force on that, right? I wasn't pushing on the wall. I didn't, So some energy came into your house from somewhere, right? Did it come from the outside or did it come from the inside? Did it come from the outside or did it come from the inside? Is it because the wind was blowing or because it got cold and then that leached some energy and then you got like a pop inside? Or was it because somebody's in the wall, there's a rat in the wall and it's got a little hammer and it's like pop, pop, pop. And it brought its own energy in, and then from the inside, it's like got the energy. When you have to define a system, a semiotic system, in terms of all the pieces of it inside, when we're trying to make claims like universe, which by definition is everything, then it's very, very hard to have what do we even mean by outside versus inside. So that's why we spent the whole last chapter talking about dissipative stuff, because you can have things that are so far away in space and time scale that it's just kind of like it's just leaving. It's kind of like it's going outside, even though it doesn't have to actually be going outside. It can just be going outside. You're close enough to you and like going off into entropically governed energy configurations into the system that it's effectively gone, even though it's technically there, but you can't even it doesn't do anything anymore. So it's not even worth keeping track of anymore. And that's sort of dissipative. So now if you became like a detective and there were pops all the time, and this is what physicists are doing, right? Not to bury the lead. And you're saying, okay, every time there's a pop, I'm going to go, but I'm stuck inside the measure. I'm stuck inside the house. So I don't know necessarily when they're going to happen, but I'm going to go wait and look for pops. And then I'm going to scope in real close, and I'm going to take measurements of the pop as it's happening, because I can do that, but I can only do it in such a way that I'm not necessarily going to catch. And that's what I talk about in the book. Like you can get in close, but when you get in that close, it's really hard to tell where energy is coming from and what part of a system, what part of the process you're in. If you want to zoom out to look for, okay, maybe this energy came down the wall. Maybe it's because the whole wall is creaking, is getting bigger or hotter or something. You can zoom it. You can do that, but you have to lose frames to zoom out and temporally. And as you lose frames, then there's this really funky, weird harmonic stuff that starts happening. We're like, okay, well, but I can't actually, I'm losing a big part of the picture because I'm losing all the harmonic frequencies that the frame rates start giving you. And I can't necessarily, and this is my theory, it's fundamentally impossible to link the big down to the small.
And this is why there's no special theory that links everything.
There's no special theory, but what you can do is you can go, all right, okay, let's say I had a really good theory of the big, and I have a pretty good engineer, it's a probability theory, and it's okay, but it's not deterministic, but I have a really good idea. Now I engineer the situation where I heated up the wall or whatever, and then I'm going to zoom in real close, and I'm going to predict where that pop's going to happen. I'm dumping energy into the system. I'm trying to predict this pop. And then when I go to measure it, it's almost where it was supposed to be, but it's not there by some weird sort of rotation and translation.
Dang, pop. Is that what a spinner is?
That's what a spinner is. And this whole thing is called gauge theory. So if the measurement is off by something that seems like a particle could have hit it and made it change, i.e. energy from inside the house, then that's we call it a non-virtual particle. It's a real particle. And there's a certain things like fermions and bosons. And if it's from outside of the house, meaning that you can never track down where it came from, because it's either temporally or spatially away, then it's a part of a dissipative energy. And that is a different class of particles. So that's like gravity and light. So the ones that have mass are particles that we can keep track of because they came from the universe, and the things that didn't are the forces that came from outside the universe. That's it. That's
light
the whole
came
thing.
from outside the universe?
Light
is the universe.
Light is the inference that we can make about how things are moving. Charged things are moving because empty space is popping. when you go to look at it. Remember how our eyes are haptic rubbing on empty space like that? It's that. Yeah.
You do talk about how space, this is part of the inflationary nature of our universe. Apparently, things are popping in and out of existence
Yes.
continuously in empty
Yes.
space. They're called like particles and antiparticles, and they pop into existence for like a second or less than a second and then immediately decay into nothingness.
What? It's so hard to wrap your head around, but
And
it's
that's
like
part of the math.
it's all part of the math, and it's all part of like because of like I was talking about earlier, keeping track of like back then and forward, and the bookkeeping has to be because there's all these weird again remember all the weird symmetries, and I'm calling them harmonics now, which is like why I talk about the eggplant and why I talk about the swimming pool because if the waves are canceling,
We all know why you
that
talk about the eggplant, Gavin. Why you want to be inside one so badly.
Right, all right. But if the waves are canceling on top of each other, then that necessarily obfuscates the way that we can infer whether that particle is existing or not. And so then when you go to infer its existence there, in order to make it make sense and be possible, you have to also infer that sort of antiparticle that popped out of existence somewhere else at a certain time because of all those weird symmetries. And it's not again, it's not it's like it's I don't even know if it's worth it to say that they aren't popping in and out of space. It's that empty space has this feature because it's all the stuff that you can't account for because empty space is just the definition of all the things that should happen but don't.
Who knew space was exhausting?
It
Okay.
is because because space is the system of semiotics that allows us to infer stuff. It's not an ether, it's not
Space
a
is
physical
the
medium.
system of semiotics that allows us to. Okay. Interesting. Cool. Who knew empty space was so full of junk?
Yeah, to the point that it's 3 degrees Kelvin. Like we can
Yeah.
measure it.
It's not really empty. It's full of particles popping in and out of existence.
The way I think about it is one of my favorite things is like empty space is not dark and the universe is not dark at all. It's screaming with information. Everything is screaming with information all the time, no matter what. Yeah, and light is quantum noise. Like when I was working on my dissertation, I had this moment when I got up really early and I was having coffee on my balcony and it just hit me like a sack of bricks. Like light is quantum noise and loud. It's
You've
loud all
been
the time.
you've been called spacey a lot as a kid and then now as an adult. It's interesting now I'm getting to hear about
Yeah.
what you're thinking about. You'll look over sometimes at Gavin and he is just clearly somewhere else.
Am.
He's down the
Yeah.
rabbit hole. And now I know he's thinking about how light is, what do you call it? Quantum blah, 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 blah,
Quantum
gibberish?
noise.
Quantum noise.
Yeah.
Sure. Whatever the hell that means. Um,
But
light
yeah,
is
you gotta
quantum
be getting some
noise.
of it by now, right? Like
Yes.
after all this work we put into reading the book.
I mean, I would like to say yes, and I think I am. I think I'm pleasantly surprised at how much I am getting. I was pretty nervous when we started this podcast, so this is just going to be Gavin monologues. Clay goes what over and over until Clay goes, I don't do this anymore. I don't know what you're talking about. I don't understand physics.
We did some of that,
Oh.
but
You're doing a good job of bringing it to my level down here in the mud where the rest of us live.
I gotta break it to you. I'm not trying to bring it to your level at all. I'm just trying to say it out loud. Like it's hard enough for me that
I guess you're a mud person through and through.
thank you, I guess.
We're all mud people. I don't know.
Yeah.
I do think it's funny that you have said multiple times that most of your colleagues who understand this stuff would be like, "What are you trying to do? Like, stop it! Just look at the algorithm, look at the theories, look
Yeah.
at the math."
Yeah. I get kind of two responses. It just depends. Some people are intimidated because they haven't spent any time thinking about it. And it is a luxury because it's just like, some people scroll TikTok and some people sit around and think about quantum dot. Like that's just how I've always been. I've always spent all my free time thinking about this stuff
Or
at some
some
level.
people scroll TikTok looking at people's podcasts who talk about this kind of stuff.
Yes, I have actually really come to love the
Hello,
TikTok
audience.
community around. No, the TikTok community around these topics is kind of amazing. There's a lot of people out there who like really want to explain and get people to understand this stuff. But I think, and we'll talk about this in the next episode, right? But it does get to like a deeper thing that For me, I'm not just thinking about the universe in like an abstract sense. And I think you did this leap too in the last episode where it's functionally very similar to the sort of consciousness problem or like brain in a vat problem, which is like how do I understand myself? How do I understand phenomenologically what this whole thing is called life and this experience and like my separation from other things? Because if I'm what it fundamentally comes down to is like if I'm at the quantum level, at the physics level, at any level, the separation between me and anything else is not real.
Indistinguishable.
It's not deterministically stable. Like I can't like go. So then, but again, that's sweeping under the rug the fact that you can measure stuff. We can all measure stuff all the time, and I can measure a pen, and I can pick it up, and I can measure you. I can see that you're thinking or bored or whatever. So that means you like yes, you have free will because I can measure that you're doing something different than me right now. So I have
Right?
to concede that, right? And just understanding that and understanding your own relationship with the universe, like I really think that the book in many ways was sort of me cataloging all the things you have to keep track of as you sort of fall asleep and your ego dies and you're like, okay, I'm going to have to keep track of these so that when I wake up again, they're still there.
I
You know
like
what I
that.
mean?
I like that. Well, so I think Friedrich Nietzsche was the one who talked about how, human beings are in desperate need of a framework of their reality. And so, for a long time, God and or religion gave people a framework. Gave them answers. It gave them, like you said, it gave them the ability to let their ego die and be like, no, when I wake up in the morning, I
It's
know
okay because
it's
there's
okay. The Earth will still be here. I
right.
didn't know it was spinning. I thought I was at the center of it. But you know what? It's fine. It didn't don't need to be right all the time in order to have a framework to function. But human nature, I think, especially when we get to higher levels of consciousness, we need more and more framework. And then at a certain point, because we started using the scientific method, Friedrich Nietzsche famously said, "God is dead," meaning like we've moved past him. We no longer need that framework in order to sort of interact with our reality. We were both raised religious, and I think both of us came to a point where we no longer, well, for me anyway, it was more of just like, there's too much of my own observation of things that led me to think that, you know what, hey, that framework just doesn't add up. The evidence isn't there for it, and the evidence is, by and large in favor of science and in the way that it explains and creates a framework for reality. But science doesn't, famously doesn't answer all the questions. Whereas like religion will answer all your questions. And it is a very nice, clean, if you have a question, it's going to have an answer. Science has lots of empty spots, lots of things that don't make
Yeah.
sense. And so
Yeah.
I think for some people leaving, a religious framework and going to like purely rely on science, it's like, this is going to be my framework for reality. I think both of us had this moment of being like, well, I need to go and find those empty spots and fill them. Because like I don't like having empty spots in my framework. And
I think you're hitting the nail on the head here. Yeah.
and so for me, I was less worried about cosmology I think than you were on that one. That one I was comfortable with. Big Bang, sure, that's an explanation enough. But for me, one that I noticed was like, okay, if I'm, if you don't believe you're the son of God, then that means you are a animal, essentially, an animal that can learn to talk. And so, okay, what makes us so special? Consciousness. What is consciousness? And so that we kind of went down this rabbit hole trying to understand it. I think I got to the point where I was like, all right, I know enough. I know enough. I filled in some of these gaps. And, the beautiful thing about science is that, it's always going to be, well, we don't know. Eventually,
Yeah.
you'll get to the point where you know as much as the bleeding, end of people in the field. And then you get to the answer of we don't know anything beyond this.
And it's
Sometimes,
okay. And
and
that's
it's okay.
okay. Yeah.
Sometimes it's because, no, you literally can't get past the measuring problem. And sometimes it's like, we still got to do more research. We still got to do, there's still things we have done, or there still needs to be a smart person to bring it all together for you. But yeah. And so like for me, I think a lot of the reasons why I get into consciousness theory and then also now cosmology, which has been fun for you, is that we're trying to fill in that framework. It
Yeah.
feels good to have a fully fledged out framework. Especially
I think it's you're right. It does feel good, but it's also just like like you talk about it being gaps. For me, it was like fill the whole space.
yeah.
Like fill the whole epistemological space and what is the biggest and what is the smallest,
You
right?
went big.
That's literally
Yeah,
what I'm
that's literally what you're
doing.
doing. Yeah.
I just to not to cut you out. I have a story about that after
Yeah, well, I was
you
just going to
finish with
say the
that.
reason I was using the term gaps is because there's this phrase that a lot of times is people will put God in the gaps. And so it's like So a lot of times, when science would suddenly explain something and there'd be a lot of evidence for it that in the past people had said, "Oh, God waved the magic wand and made that happen." They would say, "Okay, well, yes, evolution is how human beings came about, but God made it happen." So it's like they would point to the next part of science, the gap where science says, "We don't know how this worked. We know
Yeah.
how this worked. We have evidence for this and this and this. But we don't know this part." They say, "Oh, that gap, that's where God's living. Like that's where He made it work. He's the magic." That's why for me it was like, okay, those are the areas, right? Where it's like, being raised, because that was the interesting part, right? Being raised in a religious framework, they accept science and they say, yeah, science is totally right. Go to school, learn your science. You're absolutely right. Evolution's real. All these different things where 50 years ago, those same religions were saying that's absolutely not true. They sort of have to evolve with the times.
There's a little bit of there definitely was some evolution is only true
Right.
or not
Right.
really true, and there's still I mean, just the other day, somebody was saying that they don't actually believe in evolution anymore. They'd, like, gone backwards because they were
Right.
becoming more religious and
Yeah, that's fair. I mean, I went to
yeah.
BYU, and like at the time when I went, professors were very actively because I think some people raised in the Mormon Church would go to BYU and then they would be shocked and appalled that a professor would say evolution was real.
I mean, I had that experience,
Yeah,
yeah.
and so they would preface the science class. By the time I got there, it was more accepted. It's like they would preface the science class like, "Listen, I don't want to offend anyone, but when in this class, we're going to assume, that human evolution is real, blah blah blah," and
Because
we
it
would go from there.
nothing makes sense without it. It's
Right.
quite literally
And
the
so
only
for
way, yeah.
me, when I wanted to like fill in that framework, the first place I wanted to go to was the gaps because that's where I had neatly put God and said this is where God fits and this is how He
Mm.
explains the universe. And so if I'm going to let go of Him, let go of that, then
The epistemological gaps,
yes,
right?
the epistemological gaps.
Not necessarily like because there's 2 different things here. There's the one where it's I have anxiety about my everyday living my life, like just going,
Hmm.
how am I gonna tackle this next job or how am I gonna get through this like difficult period in my life? And there's sort of emotional gaps where I think what we really do is we all lean on each other. And then like the religion allows you to have a framework to have somebody to lean on. And if
Sure,
there's nobody there, then there's like a pretend person there that you can
gives you and gives
but
you a community
I think what you're talking about right now is these epistemological
epistemological
gaps,
gaps.
which is like, well, how do I understand, you know,
Yeah,
how systems work or how to navigate for me it was always like physics, how do atoms move around and how does the biology work? How does getting sick work? How does, which is where
well, yeah.
evolution
For
comes
me, it
in.
was started with the basics, where it was like, okay, one of the things that religion answers is things like, why are we here? Where are we going? And
Uh-huh.
then it's like, well, the first thing you do there is like, oh, you're framing the question wrong. Like you're taking a very human approach and applying it to something like science. And science is not that kind of framework. It's not going to give you a meaning or a purpose. That's not what it's there for. And so, yeah, but the more
I
sciencey
mean,
sides,
I would push back on that, but I wouldn't say it's what you're correct that it's not designed to do that. It's not designed to give you the framework to make you sleep better at night. Like that's not what it's supposed to do. But in my experience, like I have found an immense amount of beauty and comfort in just because like when I've learned enough about our history, like talking about like going to the Canadian Rockies and because the more I learn about the universe, the more I learn about our history as humans biologically, the more I learn about how complex cells are and proteins are and diseases are, I'm just in absolute awe of the grandeur of it. Like the inexplicable complexity of it. And it's all the more meaningful when I know that it's just stuff we're observing and we're just all putting it together and it's all just up to us to like observe it and understand it and catalog it and write it down. Like that is so like comforting to me. But it took me a long time to get there. But I can just say that science definitely plays into my framework and my identity and my humanness but in the way that, like, good music does, you know?
yeah.
Like, in the way that you can appreciate, like, a really good meal or,
Yeah.
yeah.
Absolutely. I wasn't trying to say that you couldn't find meaning in it. I was more saying that, like, it's a lot of times people will take and phrase questions in ways and apply them to things that don't make sense. It's kind of like when a kid asks you, why? But why? But why? And suddenly he's asking something that's like this weird epistemological question about the meaning of life. And you're like, well, no, that's not, you don't ask why in this situation. Because
It's not the right yeah, it's not the
it's not the right framework. And it's like, I feel like sometimes people will do that in order to try to, I don't know, not disprove or anything, but to just try to throw shade on science. You'd be like, well, science isn't going to give me a reason to get up in the morning. It's like, well, okay, sure, but that's not really what
it
it's
will,
made
though,
for.
if
It
it's
can.
paying for your career,
Yeah, right.
that's
Know,
what it does for me,
capitalism. No,
paying for my
so
family.
yeah. But anyway, that was more what I was trying to say. It was just that, like, but yeah. So I think that's kind of why I find this stuff super interesting. This has been fun, although a little disheartening at times where it's like, well, man, we really don't know crap about crap.
I want to also like we are living in an information age where we know like 99.99999% more than anybody ever in the history of humankind.
Yeah,
Like
but people were dumb. There's still so much we don't know.
there's still a lot more to know, and I'm very happy to be in that position where there's stuff
Yeah,
to learn and
absolutely.
and
Well,
we're uncovering new things, but also you should be in awe of the level of technology and knowledge that we've amassed.
yeah, absolutely. But have how much you know is if you put it in a circle and the diameter of the circle is how much you don't know. By definition, the more you learn, the more you realize I actually don't know much. That's why there's like a certain amount of people talk about how like, if someone learns a little bit about a subject, they can be insufferable because they think they know so much. But then the
Mhm.
more someone learns about something, the more they start realizing, oh, we don't know a lot of stuff. So I feel like that's kind of what I'm doing. It's like as I'm learning more about the stuff, it's like, oh, wow, I'm starting to see more and more of the edges of what we don't know. And it's
Right,
getting bigger. And
right.
sometimes that can be a little bit like, oh, I thought we knew more. But it's like, no, we do know a lot. I'm learning a lot of things that I didn't know before that I didn't know that
Mhm.
scientists had learned. But I'm also learning like, oh, wow, yeah. So there are limits to our understanding. Um,
There always will be. There always will
yeah.
be.
But no, I mean, super AI is going to come out and save the day.
We should do a special episode where we just talk about machine learning, but
People
in the
really want to know
context of
about it.
information theory, because in the book I talk about information theory because I think I correctly identified that it was like the next place where there was going to be huge advances in like how we should be thinking about everything, and but it surpassed everything I ever could have imagined, it doing. But I still think that there's a version of simulation theory that makes a lot of sense, but the simulation is not your video game style simulation. It's an inference machine. It's like a big giant, okay, the universe is keeping track of itself.
It's a
And that's
big
what
old
light is.
accountant.
Yeah, big old accountant. And we're just tapping into like the pre existing accounting machine that is like light and that starts at the Big Bang. And like, I think there's a deeper, cooler, fundamental way to think about it when you're going back to information theory. And hey, all I can say is if you're interested in that, pay attention to what's happening with LLMs
Yeah,
because it is uncovering how knowledge works. It's telling us how knowledge is structured, like
that's
how
crazy.
information is structured and can be structured, and like what are the limits of how information can be structured. And that is the new frontier. Like it is just as interesting. It's just as interesting as like fundamental physics and particle physics. I think more interesting by a long shot at this point.
Yeah, I mean, I have seen some papers and some people talking about how like we have hit the first it was a theoretical limit. Now people are saying we're actually hitting a limit of basically how intelligent AIs can get.
I think we're I think a lot of the limitations are actually just practical. I think that like they've exhausted all the data sets that they can scrape,
Mm,
and they've exhausted all the hardware, and it's like the models are not, or like the amount of information in the models is so much bigger than you could ever query, that it's just like you're just dumping stuff into the void at that point. So actually the bigger, and we did mention this earlier, the really big advances and the models that are really, really good are ones that are actually going in another direction now, where
it's the prompt engineer models.
either the prompt engineering is getting folded into the model, or if you know about Nano Banana, which is a really silly name for Google's new image
Oh yeah, I have heard of
model,
Nano Banana.
where you can say, "Hey, this is me. Put sunglasses on me and a red hat and put me like in a nightclub or whatever." And it will do it. It will consistent it knows what red hats are, it knows what glasses are. It's not like just pulling randomly something out of the ether that matches your prompt, sort of. It's like very specific directions can be taken, and you can like annotate. You can do like a whole panorama, and you just put little red boxes and be like, I want this thing to be blue. I want this thing to be whatever. I want this thing, and just write it in the image and then just like submit it, and it will do it. And it's perfect. And so people doing I saw some stuff of a guy he's like, "Oh yeah, I wanted to make like a website for a fashion company," but they hadn't done the annoying web shoot where like the shoot where you put all the clothes out and you fold them up.
Right.
He's like, "All they sent me was like the model and it was the wrong like time of day or whatever." He's like, "So I told the thing, okay, put this guy in a country club, make his coat blue, make his shoes brown or whatever."
What?
And it did that. And then he was like, now do one where it's a blue background where all those clothes are folded up on the ground in squares with like bright lighting from top down. And it nailed it. Like the seamstressness of it, like everything was like. So anyway, the reason that works as well as it does, apparently, this is all speculation because they haven't actually, like, Google hasn't released everything, but it's very fancy. It was called a multimodal transformer. But people doing operations like using Photoshop to like move a hat around, that went into the training data.
So basically, they're coming for the editor's job, baby.
Seeing the human do the stuff, and that's going into the model, and that's what's making these models capable of doing. So it really is becoming
That's
something.
wild. Well, okay, so I played around with Gemini today just because I've always just used ChatGPT, and then people are like, no, Gemini's like so much better. It's like all the different AIs wrapped into one. So I was messing around with it today, and I opened it up, and I swear like it's reading my mind because I had thought about like wanting to write a children's book for my daughter, and it just like a story mode popped up. It was like, hey, do you want to write a children's book? I was like, oh, yeah, okay, cool. So, like, I put in a little
That's kind of
prompt.
scary.
I know, right? I was like, write a children's book about my daughter and add my dogs, Morty and Echo and da-da-da. And it spit out a 10-page child's book with, and I said, do it in the style of Studio Ghibli, and had 10 images. And, like, granted, the dogs look different in every image. They consistently kept my daughter the same. They made her look similar. And I gave descriptions of what I wanted and got a general plot that I wanted to do. And it was not fantastic, but, like, I downloaded it just because, like, this is creepy and cool. And, like, I could probably fiddle with this for a couple hours. I mean, less, probably 20 minutes. And I could come up with something that was really, really interesting and good that I could print off and show, my 1 to 2-year-old daughter would be like, this is amazing.
Of course, yeah.
But, like, that's crazy. And, like, who knew that AI would come for the creatives first? Seriously, didn't see that coming.
Yeah. I don't know.
I thought the robots would take over fast food places flipping burgers before they'd come for the artists.
But they've already done that, but it's mostly in New York or like in the big cities.
Oh, really?
Yeah.
Well, not physically making the food.
This is why the chopped is so big in the cities now. The chopped salads or like
It's
bowls.
AI made?
Because you can have a robot that just like it takes the different items and it just chops them and then just spits out the bowl. Like,
That's pretty wild.
yeah. Yeah. Or
Well,
robots are doing like 80% of it. Like I forget. It's not all the locations, but one of the locations of what's the green salad place? It's so big. Anyway, it's on every corner in New York, but they all like the food prep is robots now with AI.
That's wild.
Washing the lettuce and chopping the lettuce and
Yeah. Well, I had the universal basic income. It's coming, or else we're gonna have a lot of shanty towns. It's gonna be great. All right.
Hey, should we do the song this time?
Oh, yeah. So Gavin
We
had
were gonna
another
do-
song,
Yeah.
and I will add it here.
It'll be the out. We'll use it to play it out. You know,
we'll
People
play.
made
We'll
it to
play
the
it
end
out,
of the
Gavin.
podcast.
We'll pick one of the happier ones. Doodle-doo-doo. Just kidding. They're all happy.
No, they're not. Some
All
of them
right,
are not
well,
happy at all.
Big gulps, huh?
And I'm happy about that.
Like and subscribe.
All right.
We're going to get 1 million views.
Ciao, Bella.
And that's a wrap on episode 7 of I'm Finally Reading My Brother's Book. Today we shined a light on the darkest parts of the cosmos, dark matter, dark energy, and the limits of the stories we tell ourselves about the universe. If you enjoyed this conversation, don't forget to follow the show wherever you listen, leave us a rating, and share it with your friends. Now we get to enjoy a preview of a song by Gavin. Here is Inside Out.
1, 2, 1, 2, 3, 4. Inside out, upside down, you know the world keeps spinning around. Front to back and side to side, all these thoughts keep spinning around. What the hell am I running from? When it happens every night, it's gotta be something. And I swear the barrel and the gun up was gone. So just sit for a spell. I guess it's how it feels that makes it real. I guess it's how it feels that makes it real. Front front to back and side to side. What if everything you knew was a lie? Take your time, don't roll it back. All the best parts are still intact. The lines around your eyes are worth about 1,000 times what it took to earn them. And I don't know what's coming next, but I bet it's alright. I guess it's how it feels that makes it real. I guess it's how it feels that makes it all so real. Oh, I feel it coming around. Oh, I feel it coming around. I guess it's how it feels that makes it all so real. Inside out, upside down, you know the world keeps spinning around. Front to back and side to side, you lose the plot but find your light.